Hello everyone. My name is Arthur Su. Today I'm going to do a quick introduction to computer programming. I do this program for teaching my own children coding, and I think my class is slightly different than what being provided on the market, and I'll try to give a my own style of how to do that. First of all, who am I? My professional experience can be found in LinkedIn. I currently work for Google, and I am working on the project which brings Android apps to Chromebooks. Uh, my work is right now. My daily work is not really programming or writing code. It's more like leading a group of smart people to help deliver the product. And before that, I am a professional working in C++ and JavaScript for years, and I also work on a Java related project in my in the early stage of my career. So before we start, what is a bug? So this is the first computer bug ever found in 1947. So basically, a bug fly into the computer at that time and cause the computer to malfunction. So from that day on, everything that going wrong in the computer world, we say, okay, there is a bug. So what should we expect from this class? Say, basically, uh, I believe everyone's code has bugs, including their slides or their documents talking about it. So this sets of slides and lectures will also have bugs. And I expect the bugs to be found and corrected through iterations. So I will keep updating this slide deck when I have time. So, and therefore, please look into version history for the changes. And this is the beauty of Google Docs. Well, videos, once I record it, it will be harder to change. So we will use the content in the latest slide decks as the ground truth. And I am not a native speaker of English. I may make a lot of grammar errors. My pronunciation will have accents. Sorry about that. And I probably will not be very diligent fixing those bugs. And my approach to teach programming, I'm giving a lot of content besides programming to establish the big picture. I usually do it in the depth first. Means that I will give you an overall picture. Then I start digging into each small point. So what do I mean by the big picture? The big picture usually is like what can programs do? How do programs run? Where can I use programs? I start from here to try to give you concept. Okay, what can computer programming do, and how it affects our lives? And if I want to pursue for that profession, what should I know? And this will have a lot of overlaps with CS 101. If you already are familiar with those, feel free to skip the content, and also feel free to review them with my lectures if you're interested. So, what is computer programming? First of all, for most people, when they first get into the CS world, computer is just like a big black box. And what we can treat this computer thing is that the computer is a black box that takes input and generate output. This is very abstract. So let's take a game as example. Say when I play Pac-Man, okay? The Pac-Man actually have input, which is your joystick or your keyboard, and you try to move that Pac-Man and dodge, eat the cherries, and try to dodge the ghost. Okay, the cherries, the ghost, you see your Pac-Man moving. It's actually an output on the screen. So the computer actually say, okay, I detected your joystick moving to the right, so I move your Pac-Man to the right, and that is basic saying that computers do everything. Computers take input and generate output, and we try to abstract all the computer functionalities into that. So what does computers have? So we talk about input and output. So your input probably most intuitively the human interface. For example, your keyboard, mouse, joystick, remote control, even latest the voice input. If you happen to have a voice control like Amazon Echo or the Google Home at your home, then you will see they can take a voice command. These are also human interfaces. And it also can come, which is not that obvious, come from the network. For example, someone call you, say like, okay, someone sent you a text message, right? And the computer takes the input and it has these building blocks, which we'll explain in later slides. It try to run the programs and it will output the process result to either the display, which means the screens, either your phone screen or the PC screen or your TV. Audio devices may be like a response to your asking, or send it back to network, and so on and so forth. So for example, let's take a look at Google's Pixel 4 phone. So this is Pixel 4 phone, and when you browse the website or go to the Google store, you see, oh, Pixel 4 has a spec. A lot of people don't have the concept that the modern smartphone is actually a computer. Why? For example, you see this. It has a Qualcomm Snapdragon 855. It's a 284 gigahertz, blah blah blah, octa core. What is that? That is actually a CPU, the CPU spec. And Adreno 640, what is that? This is actually the GPU block, and it comes with 6 gig memory. This is its main memory, and 64 gig or 128 gig, that is actually the storage. So you see, as in the computer block, it has CPU, GPU, memory, and storage, right? And it has input, the camera, sensors, your SIM card, your wireless and location sensor, your network connectivity. These are all IOs. So we talk about CPU, and what does CPU have? So CPU usually is also called as a processor. All right. This processor and everything inside your computer is driven by a clock. So this processor actually talks to other parts like a memory, like peripheral. Peripheral means the I/O ports we have here, and maybe the storage stuff. And they talk through it through bus and controllers. So we see the DMA controller, interrupt controller, bus interface. So if you're really interested, I would suggest you go for the computer architecture classes, and they will have more detailed elaboration on how the modern processors have been built. But as a programmer, you do need to know the fundamentals of how the CPU interacts with the other part of the computer system. So first of all, clock. A lot of people, they learn programming and they don't know how the clock works, and this is quite interesting. Say basically why clock is important. So this involves the fundamental of how the CPU execute your code. The CPU will load one or more instruction for each tick of clock. And remember, your clock is fixed. A processor, when it's designed, it has a fixed clock rate. Your GPU also have a fixed clock rate. That means each cycle, this length, the length of time of each wave is fixed for that processor. Say for example, if in the past example we have Pixel 4 CPU, it has 2.8 gigahertz, means that every second there will be 2.8 giga ticks. inside it. So that's why it's called 2.8 gigahertz. So the CPU may have some special thing. For example, Intel processor superscalar. What does it mean by superscalar? It means that the CPU can load more than one instruction per clock tick. So what is an instruction? Instruction means that the CPU can run one very basic operation based on your command. Okay, and so each execution unit for running instruction is called a thread. So this thread will be a very important concept we will talk about later in the more advanced programming. But so far, the definition is like a thread is a unit that can run the instructions. So modern chip manufacturing allows putting multiple CPUs on the same die. And so each CPU, we call it a core, right? Because they are sealed within a chip. So you can no longer say, okay, one chip is one core. Instead, you say, okay, every chip is multi-core CPU, which means that they will be able to say if there are 8 cores in one clock, they will have at least 8 threads that can run your code. And sometimes we will see terms like big core or small core. Big cores are usually more powerful CPU but drain battery faster, and they usually have way higher clocks. Or a small core, which means a less powerful CPU but drains battery slower. So almost all modern CPU chips are multi-core. So we talk a lot about the instruction. What are instructions? Say this is a sample of a very old CPU called 6802. What are instructions? So the instructions are machine code. So these binary in their hexadecimal form is like every clock cycle. Okay, every clock cycle, say tick, it loads this C000, and tick, it loads the next one, and tick, load this one, and tick, load this one, and tick, load this one. So every clock tick, it loads one step. Okay, and these steps are called instructions. And what the CPU see is actually these binary forms, which only the machine can understand. That's called the machine code. Now, machine code is actually generated from assembly language. Okay, so some people consider it's human readable, maybe. Okay, so the assembly language is a fundamental base that you can achieve that, but that's not the only way to generate the machine code. So let's back a little bit. So to generate the machine code, usually what we do is to use a programming language, and these I will detail a little bit later. So then inside the CPU, we do have two very important concepts. You might not be using them in your programming languages, but it will be very nice for you to understand the basic concept. First, register. What is register? Register are some super fast memory used by instruction. For example, I want to add two numbers together, right? The CPU have to have somewhere to hold those data. And those data can be put in the register so that CPU can directly add these two numbers together. And what is stack? Stack is a first in, last out memory. Usually we say CPU runs stuff line by line, right? So what if, say, okay, we tell CPU, do A, do something, work, and then we suddenly say, oh no, before doing finishing A work, I need to do B first. So that happens, right? Say, okay, before I am able to fry a chicken, I need to heat my oil first, right? But I need to move from my chopper board to the stove. That's a metaphor for it. So what can I do? In the computer world, we say, okay, let me push my current states into stack. and move the CPU to do B first. So CPU then move to B, do B, and work, and B is done. Now, okay, B is done. My last task is what? I don't know, right? So I pop my last state from stack and say, okay, my last task is A. So I go back to work on A. So these are the built-in hardware stuff inside your CPU. And bus and standards, a bus is a communication system that transfer data between components inside a computer, and the controllers are moderators or arbiters of who can use this bus and when. And modern computers use standard for hardware buses, say like PCI, DDR, SATA, USB. These jargons usually means a hardware communication protocol, and they're actually mostly used on buses. So the beauty of these standards is that they allow different vendors to provide components that can interconnect. And these components are also controlled by programs. So when we're talking about programming, it's not just limited to, oh, I write an app, I write a game. In fact, inside your computer, inside the hardware, there are also software programs controlling important stuff. And usually we call these programs firmware. There's something in between the hardware, the actual chipset logic, and the software pure program you run like a Pac-Man. So the next block we talk about computer is the main memory. And in computer, here is a very important terminology. We usually refer the main memory as the heap. So why do we need the main memory? The main memory is because the registers and stack usually have very limited size. They're very, very small. We count them in bytes. And modern computing require more data than that. So for example, a cat meme can easily require 1 megabyte just to show the cat on your screen, right? So you need some fast memory that's not in the CPU, but that CPU controls it, so that you can have your beautiful cat meme shown there. So why do we call it heap? It actually has nothing to do with the data structure heap if you already have taken the data structure class. In fact, the heap here means a pile of memory, and that's it. And because we said it's a heap, so we allocate and deallocate the memory, or say we allocate the heap, or we deallocate the heap. So the amount of memory you can allocate is directly related to the address bus width, which usually is referred as a CPU's bit count. That is a not so accurate description, but generally is true. So for example, when we say a CPU is 32-bit, that means it only can control 4 gigabytes of memory for a given process. But for 64-bit, wow, that thing go crazy big, like 16 exabytes. So memory management is actually way more complicated than just like, oh yeah, CPU control memory. No, the modern computer system has way more sophisticated way to control the memory. And no matter you learn like auto managing memory programming language like Java, or you learn some languages that allows you to control memory like C++, if you are determined to become a professional programmer, you really need to learn and master the memory management. It affects how your program is run and how performant your program can be. Whether you use Java or C++, that doesn't really matter. You have to know. So I can briefly talk about this. The modern operating system, they actually have the running program see virtual memory. So basically your program will see, oh, I have the heap to use. But underneath, they use paging, they control the physical memory, they even swap some blocks to the hard drive. Okay, so that's way more complicated than that. If you're interested, I believe the operating system class will have a very detailed section for this. And next, what is a GPU inside a computer? The GPU is usually a specialized chip for processing the graphics. For example, you play like a first shooter games like Halo or like other like very graphics intensive games. These require special geometric or physical engine to make the game looks better, looks more real. And in this case, usually you need the specialized computer chips to do that. And we call that kind of chip called GPU. And many modern processors integrate the CPU and GPUs in one chip. For example, the recent Intel chips, they almost like a pack, they almost all have a GPU pack inside them. So GPUs, besides doing graphics, they actually are very widely used in video decoding, encoding, machine learning, and scientific computations. Next, we talk about storage. So we say, okay, there are registers. You might heard of CPU cache. If you're interested, computer architecture will tell you what that does. Main memory, we talk about it. These three are usually some chips that's within your computer, your cell phone. Then you might have local disk. Local disk these days may also show in the IC form. For example, your SSD drives. That looks very like a RAM stick. But it also can contain like a legacy, like hardware drives, those mechanical ones. And the bottom of this pyramid is the remote storage. For example, you can always have Google Drives that store in the cloud. So why do we have so many different storages? Because on the tip of this pyramid, the speed is faster, and we are usually talking about order of magnitudes faster, which means that registers and cache usually are 10 times faster than main memory. Main memory usually is 10 times faster than local disk. Local disk usually is 10 to 100 times faster than your remote storage. However, on the other hand, register and CPU cache and main memory, they are very expensive. Local disk costs some money. Remote storage, a lot of remote storage free, almost nothing. So this become like a trade-off. Why? Because when we write programs, the almost like a half or more of the time we're handling data. Where do you store data is a very, very important topic, and we always trade off things between, do I want things to run faster or do I need to use more? And they are conflicting. We need to make that trade-off, the judgment call. So here I'm just trying to let you know, we as a programmer, majority of your time, or say as a professional programmer, majority of your time is to find the best way to solve your problem. And your problem is not necessarily always say, okay, I want to make my code run faster. A lot of time you probably need to sacrifice speed in exchange to gain more capacity. And that is why programming becomes so hard. So are you lost now? All right, fine. I think I talk a lot, and let's roll back and see a very simple thing. Say, okay, here is a calculator. Say, let's assume you have an Android phone. You have a calculator on top of it, right? So how does that calculator run on my phone, right? You download the calculator app from the Play Store, you install it, you open the calculator, you click button 1, button plus, button 1, and you press the button equals to. then you will see 2 on the results, right? Say, let's dig. These two, how do these two happen, right? How do the highlighted part happen? So the calculator program is loaded into memory by Android. Android is an operating system, or we say OS in our example. And like Linux or Windows, iOS, they're all operating systems running on different machines. Say, in our example, we take Android because I'm more familiar with it. Now, Android runs this app and let it draw assets on the screen, which are the buttons, little graphics, right? You touch the screen, right? And these will generate events in Android. Android forward these events to your calculator program. Say you press button 1, right? Android will tell your program, oh, this little button has been pressed. So your calculator get these events. Oh, button 1 has been pressed. Now I know 1 is pressed. Now the plus button is pressed. Now you know the plus is pressed. Then 1 is pressed, you know 1 is pressed. So your app eventually know, okay, there's a sequence 1 plus 1. And when you press the equals, then your calculator of course knows, okay, it's time for me to calculate the result and get the answer and draw the answer on the screen. So how do my calculator app calculate the value of 1 plus 1? So calculator app is written in Java. If you're an Android app, chances are it's written in Java, all right, or Kotlin, but that's still considered Java compatible. So it's written in Java or some high-level languages. And what did high-level languages do? Say the programmer maybe have int plus up 1 up 2 and return operator 1 plus operator 2. This is usually what the programmers see, human readable. Say basically, okay, I have something that can take 2 operands plus them and return. So this code inside Java, it has to be compiled into an Android DEX format pack in an APK. So you don't really need to know the details for now, but you understand, oh, this will eventually be magically packed in a file. Okay, this file has been uploaded and by the developer to the Play Store, and you download it. You install this app. So the Android, when its APK is downloaded, it will run a program called DEX2Alt to native code. So basically, it will what native code means is that it's something that can be directly loaded by Android OS without additional transformation. Okay, so when Android load that native code, it start running, and your function eventually, say the plus 1 plus 1 will be called when your program calls it, right? But right now, the function is already in the machine code format. So it will call your phone CPU and to run it. So what does that machine code do, right? Oh, so this is what you see in Java program. It's a very high level, and it will be eventually through several transformation and become this machine code form. Say, okay, load operand 1 into register R0, load operand 2 into register R1, add R1 into R0, return R0, the result requested. All right, so clock 1, load this, clock 2, load this, clock 3, load this, clock 4, return. Bam, done. So clocks keep ticking, and your instruction load and run one by one. And the results are calculated according to the program's design. So I hope this gives you a quick dive in about, okay, how your program is designed to do and how the CPU and everything together runs it. So your program's lifecycle will be more like on a development machine. You write some code, compile, link. If you need to debug, make sure it's almost bug-free, and you pack it into an APK packages and you upload to the Play Store, and the Play Store will say, okay, do you do something bad? No, then it lists, and for someone to download, maybe you can charge some money, earn a little bit. from it. And your customers download your package, install and run on their cell phones, right? And we have most developers need to use some libraries. We cannot reinvent every wheel ourselves. We'll talk more about libraries and this whole process, especially the yellow highlighted part. And also there are feedback steps. So this is what a programmer usually deal with for the modern app ecosystem. So that will conclude our first session, and hopefully this give you a good start of information to start with. And our next will be to set up a working environment for you to really learn the programming.